Okay, so let's start then. Okay, so this is the statement of the Carter and Hadamard theorem. It says that if n is complete and simply connected and has non-positive sectional curvature everywhere, so that means at all points and in all directions, P and sigma, the sectional curvature is less than or equal to 0. Remember here, sigma was a two-dimensional subspace of the tangent space. So this is true for all points P and for all two-dimensional subspaces sigma in TPM. Then if I take any point P, if I take the exponential map based at P, then this from the tangent space TPM to M is a diffeomorphism. In other words, M is therefore diffeomorphic to Rn. Okay, so this is quite a surprising, well, a nice theorem in the sense, what it says is that you see curvature influences topology. In the sense we're starting out with something which is just simply connected, right? So simply connected plus non-positive curvature. So if I make this curvature assumption that the sectional curvature everywhere is less than or equal to 0, and I need completeness also, then it implies that M is diffeomorphic to Rn. In other words, in particular, M is contractible, right? So this implies contractible. Is this clear? Yes?
Yes, sir.
So, for example, if G is a Riemannian metric on Sn, the n sphere, n greater than or equal to 2, then Sn is simply connected, but it's not contractible, right? Yes?
Yes.
Because it has a non-trivial homology in n dimension n. That's one way to see that it's non-contractible, right?
Yes.
Okay. The top homology is Z. So, then what can I say about the curvature of any Riemannian metric G on Sn?
It has to be positive.
At some point, right? So there
Right,
is
right.
P in M and sigma in TPM. Such that Kp sigma is strictly positive, right? Is this clear?
Yes.
Because otherwise, if it was less than or equal to 0 everywhere, then it would become diffeomorphic to Rn, but Sn is not homeomorphic to Rn, right? Rn is contractible, Sn is not. So, okay. Is it clear? Yes? Okay.
Sn is compact, Rn is not.
Sorry?
No, I just said that Sn is compact, Rn is not.
Yeah, or Sn is compact, Rn is not, sure. But Yes, yes, Sn is compact, Rn is not, right? There you can also just say it from there. Yeah, sure. Correct, correct, correct. Or I mean, or even if you take, let's say, uh, something non-compact. So same statement. If G is a complete metric on Sk cross, let's say Rk minus 3. Sorry, Sk cross Rn n minus k. Sorry, Rn minus k. So here this is not compact. So I can't use compactness as an argument. Okay. But this is simply connected, right? If k greater than or equal to 2.
Yes, sir.
This is simply connected because Sk is simply connected. And but this is not contractible, right?
Yes, sir.
Right? Because Sk is not contractible. So this will not be contractible. So now I have to use contractibility as the argument, right?
Yes, sir.
Or I mean homology groups or whatever you like, but yeah, I mean some other topological invariant, right? Okay, is this clear? So any metric on such a manifold has to have a point of positive curvature. So basically, as long as M is simply connected and not contractible, it has some non-trivial topology, then that non-trivial topology will force there to be a point of positive curvature. Okay. All right. Or in other words, if you have curvature less than or equal to 0 everywhere, then the topology has to be trivial, right? It has to be the diffeomorphic to Rn. Okay, it has to be diffeomorphic to Rn. So let's start doing the proof. So the first lemma is so M is complete and Kp sigma less than or equal to 0 for all P and N. Sigma in TPM. Gamma is a geodesic in M. Then for any Jacobi field, J along gamma. So remember, J gamma was our notation for the space of Jacobi fields along gamma. The function f of t equal to norm jt squared. This is a convex function. Okay. So maybe I should so also so maybe I should break this into two parts, 1 and 2. For J in J gamma, if J0 is 0 and J prime 0 is non-zero, then Jt is non-zero for all t in R, for all t not equal to 0. Okay, so the proof is just a simple computation. So f of t is the inner product of Jt with J, right? Of J with itself. So what is f dashed? F dashed is going to be by the compatibility with the metric. It will be 2 times inner product of J prime with J. Yes? Right?
Yes.
And now again by compatibility with the metric, f double dash will be 2 times. So when I differentiate this, first I get a J double dash with J plus I'll get J dashed, right? So that will give me norm J dashed squared. Okay. But now I get to use the fact that J is a Jacobi field. So I know what J double dashed is, right? J double dashed will be minus R of gamma prime J gamma prime, right? Yes? Right?
Yes.
By the Jacobi equation. Okay, so so what is this quantity? By the definition of sectional curvature, right? This is going to be 2 times minus the sectional curvature at the point gamma t of the span of gamma prime and J, right? Into mod gamma prime wedge J squared plus norm J prime squared. Is this clear? Right? Yes?
Yes.
But k is less than or equal to 0. So minus k is greater than or equal to 0. And this norm squared and this norm squared are greater than or equal to 0. So the whole thing is greater than or equal to 0. Okay. So f double dashed is greater than or equal to 0. So f is convex. Is this clear? Okay.
Okay.
So there's just one case you might say, what if J and gamma prime are linearly dependent, right? Then note, if gamma prime J are linearly dependent at time t at some point, then by R gamma prime J gamma prime J, this will be 0, right? Because J will become some multiple of gamma prime. So this becomes gamma prime, gamma prime, gamma prime, gamma prime, right? Times a constant. So that's 0. Is this clear? Yes?
Yes.
So we still have, F double dashed greater than or equal to 0. Okay? Is this all right?
Yes.
Yes, is this okay? All right.
Yes, sir.
Okay, fine. Okay, so for part 2, if J of T naught is equal to 0 for some T naught not equal to 0, then F of T naught is 0 and also F of 0 is 0, right? Because I'm assuming in part 2 that J of 0 is 0, right? I have to show that then J prime T is non-zero for all T non-zero. If J prime 0 is non-zero. So see, J prime 0 non-zero just means that J is not identically 0, right? Because if J0 is 0 and if J prime 0 is also 0, then by uniqueness of the solution with initial conditions, J will become identically 0, right? So J is not identically 0 if and only if J prime 0 is non-zero, right? Is that clear? Okay.
Okay.
Yeah. Okay. So all right. So here, if J T naught is 0 for some T naught not equal to 0, then F of T naught is 0 and F of 0 is 0. So if I is the interval joining T naught to 0, then F of T is less than or equal to 0 for all T and I by convexity. Right? Because at the endpoints it's 0. So by convexity, F of T is less than or equal to, you know, alpha, a convex combination of the values at the endpoints. Right? So F of T is less than or equal to 0 by convexity for all T in this interval. Is this clear? Right? And F of T is greater than or equal to 0 for all T and I, because F is norm squared. So that means that F of T is 0 for all T and I, and F is the norm squared. So that means that J of T is 0 for all T and I. But 0 belongs to the interval I. So therefore, if J is constant 0 in the whole interval, then that means that J prime 0 is 0, right? Yes? So that's a contradiction. Is this clear? Yes.
Yes, sir.
Okay. Yes, Utshab, Nobo, Kiran, Roshan, is this all right?
Yes, sir.
Familiar?
That's fine.
It's fine. Yeah.
Yes,
Okay.
yes.
Okay. So as a we get therefore as a corollary. So M as about so M complete. So I'll just write complete of non-positive curvature. Okay. And P and M. Then XP. What we get is that from TPM to M, this is a local diffeomorphism. Okay. So we need to show that for all V and TPM, the derivative of XP. So enough to show, let me say, well, let me say enough to show the derivative of XP at V from TPM to T of XP VM is 1-to-1, right? Yes. Okay.
Yes, sir.
Then the result will follow from the inverse function theorem, right? Okay. Then result follows from inverse function theorem. Okay. So if V is equal to 0, then I know that the derivative of the exponential at the origin is identity, right? So we're done in this case. So assume V not equal to 0. And let gamma T be XP of TV, the geodesic with initial conditions V, P and V. Okay. And so given let W be an element of the tangent space to TPM at the point V. Or let me write it as, okay, fine. Let me write it as an element of TPM which I identify with the tangent space to TPM at the point V, because TPM is a vector space. Okay, and suppose W is non-zero. Okay, and let J be the unique. So then we know how to calculate the derivative of the exponential acting on the vector V, right? It's given in terms of the value of the Jacobi field at 1, right? Where J is the Jacobi field along gamma, such that what? What are the initial conditions of J? J0 is? What are the initial conditions of J? J0 is something and J prime 0 is something. What are they? So remember how we got the derivative of the exponential map, right? Yes, what will the initial conditions of J be? Anyone? Anyone?
J0 equals to P and J prime 0 equals to V.
V.
Uh,
V is equal to gamma prime, right?
right.
Look, here's your picture. Just remember this picture. This is V. And now I'm changing V to V plus SW, right? So then I'll get a one parameter family of geodesics like this, right? Yes?
Yes, yes.
So this is V plus SW, right? So what will, when I differentiate this, what will the J0 will be 0, and what will J prime 0 be?
W.
W, right? Okay. So then dx P at V applied to W is equal to what? What is this in terms of J? Well, remember how the exponential works. You flow for time 1, right? This is time 1, and then you flow for time 1, and then I'm differentiating it with respect to S, right? So the derivative should be this vector here. What is this vector? If this is gamma of 1 and this is gamma of 0, then what is this vector here? When I take DDS at S equal to 0 and T equal to 1, what vector do I get here? What is this vector here? Anyone? This is? Yes, are you there?
Yes, sir. I'm trying to think.
Look, I'm just
J
flowing
prime
along.
0 1.
Sorry?
J prime of gamma 1.
What do you mean J prime of gamma 1? What is this vector? This is, look, this is the geodesic gamma S, this is the geodesic gamma 0, and I'm taking DDS of gamma S T, right? So what is that vector? DDS of gamma S at 1, right? What is this vector here? What do I get when I differentiate a one parameter family of geodesics? I get, if I take del S of gamma S T, what do I get? Yes? Anyone?
Choose J1.
Right, just J1, exactly, just J1. We did this recently, right? Have you forgotten? Yes, we did the derivative of the exponential map is given in terms of the value of this Jacobi field at 1, right?
Yes.
Do you remember, all of you? Okay, let me go back a few classes. So it seems you've forgotten everything already. So where is it? Yeah, see, look here. You see this? Right? If I take an initial point P and a tangent vector V, and I take W in TPM, which is the tangent space to TPM at V, and then I take gamma as the geodesic with initial conditions P and V, and I take J to be the geodesic Jacobi field, such that J0 is 0 and J prime 0 is W, then the derivative of the exponential at V acting on W is J of 1. Is this clear? Yes?
Yes.
Okay, and what is the proof? Look, here the exponential is you flow the tangent vector for time 1, and then you apply the projection, right? It is pi composed with phi 1, right? Yes?
Yes, yes.
So what is the derivative of the exponential at V acting on W? By definition, this is DDS at S equal to 0 of XP of V plus SW, right? By the chain rule, yes? Now, what is XP of V plus SW? This is pi composed with phi 1 of P comma V plus SW, right? Yes?
Right.
So by the chain rule, this is d pi at phi 1 of theta applied to d phi 1 of xi, where xi is equal to dds at s equal to 0 of P comma V plus SW. So this belongs to T theta Tm, right? So d pi theta xi is 0 because all of these have the same foot P. So pi is constant along this curve. And since this is in the same tangent space, k theta xi is just the ordinary derivative in DDS of this curve in TPM. So that is just W, right? So, and we know that d pi composed with d phi 1, the differential of the Jacobi of the geodesic flow is just the Jacobi field J at 1, right? Where J0 is equal to d pi theta xi, which is 0, and J prime 0 is k theta xi, which is W, right?
Yes.
Okay. All right. So that's it. Okay. So in our case, what can we say about J of 1? We know that J0 is 0 and J prime 0 is W, which is non-zero. So by the previous lemma, what can we say about J of 1? What can we say about J of 1? It is, so if J prime 0 is non-zero and J0 is 0, then what can I say about J of 1? Anyone? What is the previous lemma that we just proved? Look, what did we just prove now? If J0 is 0 and J prime 0 is non-zero, then JT is non-zero for all T non-zero, right? So what can we say about J of 1?
Non-zero.
It's non-zero, that's all, right? It's non-zero. And that's all we need, right? J of 1 is non-zero. Tells us that the exponential map, its derivative is 1 to 1, right? I took a non-zero vector, its image is non-zero. Yes?
Yes, sir. Yes.
Okay, so that's it. So we're done. Okay, so note, M complete non-positively curved implies what the earlier lemma says actually is that any Jacobi field can vanish at most once if it is not identically zero. Right, that's what the earlier lemma is saying basically. Yes?
Yes.
Okay, because the point is, see, if this is my gamma and I take my Jacobi field, so basically it's, so suppose the Jacobi field vanishes once here, right? Yeah, so if it vanishes again somewhere here, so we've got less than a minute, okay? So so let's stop the meeting and we start again, okay, in another meeting. So let me stop this.